Jai Hind students, how are you all? I hope you must be all in very high spirits, right? Students, motivation is your desire to do something with your personal life, at work, in school, in sports, or in any other hobbies, right? Which you love to do during your leisure time. Having the motivation to do something can definitely help you achieve your big goals and dreams, whatever they may be. And students, there are 3 simple tricks to keep yourself motivated. First is to create a positive environment around yourself, right? Second is to make yourself surrounded by motivated and positive people. And third one, which is the very important one, is try to celebrate your each and every small wins as well, right? So students, with that, let's begin this session. In this session, we are going to discuss some very interesting points. We'll discuss the motion of a vehicle while taking a circular turn in various cases. On a level road, then we'll discuss the banking of tracks with friction, without friction. So we'll be dealing with these 3-4 cases in this particular session, right? So first and foremost, we'll discuss the case of the motion of a vehicle on a circular road when it is level, when it is horizontal, level circular road, right? So students, as you are aware, when a vehicle, it may be a car, a bus, a truck, or a van. Here I have tried to draw a van, right? So whenever a vehicle takes a circular turn, right, on a level road, then what happens is the wheels of the vehicle tends to go in the radially outward direction. It tends to move away from the circular track. So in order to keep the vehicle in its position, centripetal force must be required. And you know students, centripetal force is that force which always acts radially inwards, right? So the force of friction between the road and the tire surface, that provides the vehicle the necessary centripetal force, and it prevents the vehicle from going out of the track, right? So this concept will be used over here so as to find out the expression for the minimum velocity which this vehicle under consideration can possess so as to execute a circular turn on a level road without skidding, right? So let us consider this to be a vehicle, say of mass m. So suppose this is the center of mass of the vehicle. So its weight m into g will obviously act in the vertically downward direction. So this is where the weight of the vehicle will act, right? This is m into g, right? And in the diagram I have shown these 2 tires, right? So as I stated, while taking a circular turn, the tires of the wheels or the vehicle itself will tend to move in the outward direction, right? And that is being prevented by the force of friction which exists between the road and the tire surface. So students, the force of friction will act along this direction. Suppose this is F1 and there is another force of friction. It can be considered to be like this. This is F2. So F1, F2, in the diagram I have shown only 2 tires. So F1, F2 are the force of friction between the tire and the road surface which acts in the radially inward direction. This is a circular track. This is the inner one and this is the outer one. So suppose this is the center. So this will be the radius, isn't it? This is the inner radius and this is the outer radius. We'll consider small r to be the mean radius. If Ri and R naught are the inner and the outer radius respectively, then the mean radius of the track would be given by obviously Ri plus R naught divided by 2. So we will consider this to be the mean radius of the circular track, right? Okay, we were discussing the forces acting on it. The vehicle is on the level ground, so the vehicle will experience a reaction force from the ground, and we are aware, students, normal reaction, it always acts perpendicular to the surface on which the body is placed. So since it's a level road, so reaction force would be perpendicular like this to the level road. This is the normal reaction. Now it can be divided into two parts, this one and this one. These are the two parts. So here it can be considered to be reaction force R1, and here it can be considered to be R2. So net reaction force, it is R1 plus R2. I hope diagram is pretty clear, isn't it? Now students, as I've stated, again this is a very, very important statement. The force of friction that exists between the tires of the vehicles and the road surface will provide the vehicle the necessary centripetal force, right? So while taking the turn, suppose the velocity of the vehicle is v, and as we have discussed, the radius of the track or the radius of the circular turn is r, then centripetal force would be mv square by r, and that is provided by this force of friction that exists between the road and the tire surface, isn't it? So F1 plus F2, it acts along the radially inward direction. Whenever force acts along the radius in the inward direction towards the center of the circular track, then the nature of that force must be centripetal, right? So it should be equal to centripetal force. Its formula is mv square by r. At the instant when it is taking a circular turn of radius r, suppose its velocity is v, so mv square divided by r. R is the radius of the circular turn or the circular track under consideration, right? So put this as equation 1. Also students, we are aware, as per the laws of friction, F1, it is equal to mu into R1, isn't it? Mu is the coefficient of friction, obviously, and F2 is mu into R2. Mu is again the coefficient of friction, which will depend upon the nature of the surfaces in contact. In this case, the tire and the road surface, obviously, right? So substitute these values over here. Therefore, mu R1 plus R2 is equal to mv square by r, or mu, what is R1 plus R2? It is the net reaction acting on the vehicle, mv square by r. That is, mu, r is equal to mg. The vehicle do not possess any motion in the vertical direction. So in the vertical direction, the body is under the influence of balanced forces. So the total weight of the body when it is placed horizontally is exactly balanced by the reaction force. So r is equal to mg. Right here, r is equal to mg. You can put it as equation number 2. So it is equal to mv square by r. Therefore, students, v square is equal to mu gr, or v is equal to square root of mu gr. Right? So this is the expression for the maximum velocity which this vehicle can possess so as to execute the circular turn on a level road without skidding. Right? So mathematically, it is more appropriate to write the result by using inequality. V should be less than or equal to square root of mu gr. So this is the proper mathematical representation of the fact that this velocity is the maximum velocity which this vehicle can possess so as to enable it to execute circular turn without skidding. Right? So this is case 1. So again I repeat, students, the most important point to be noted is that the force of friction that is being provided by the tire and the road surface, that exists between the tire and the road surface, that provides the necessary centripetal force, right? and it is this centripetal force which enables the vehicle to take a circular turn, or which enables the vehicle to execute the circular turn. So when after prolonged use, the corrugation in the tires recedes, isn't it? So as a result, the force of friction deteriorates, or on a slippy road, the force of friction deteriorates, so mu becomes less. So in such a case, the speed of the vehicle would be much smaller, with which it is required to execute the circular turn on a level road. So friction plays a very, very important role, right? So in rainy seasons, while driving a vehicle, especially in hilly areas, it is absolutely mandatory to maintain a small speed, which is less than that of mu gr, square root of this term, while executing a circular turn on a level road, right? So we are over with case 1, right? Okay students, now let's consider the second case, that is banking of curved road, and in this case we will consider the force of friction to be negligible. Students, force of friction is not a reliable force because it depends upon the nature of the two surfaces in contact, isn't it? On rainy days, as I've told you, or on soapy surface, or when the surface of the road, suppose oil is spilled on the surface of the road, then the force of friction reduces to a great extent. So force of friction is not reliable, right? So in order that a vehicle can execute a circular turn at a reasonable speed, the outer edge of the circular track is slightly raised as compared to the inner one, and this is known as banking of tracks. Okay, this is the inner edge, while this is the outer edge of the circular track, right? Now this outer edge is slightly raised, say by height h, with respect to the inner one. So this is known as banking of tracks. And we will discuss in this article how banking of tracks will enable a vehicle to take a circular turn at a reasonable speed, right? So in the case when we are considering banking of curved road, in this sub case we will consider the force of friction to be negligible, right? So this is a vehicle. Here I have tried to draw a car. In the previous case I have tried to draw a van, and this is car. Suppose its mass is m, right? This is angle theta. It is known as angle of banking. Theta is known as angle of banking. Angle of banking. Right? And this is the width of the road. Suppose it is B. B is suppose the width of the road, and h is the height through which the outer edge of the circular turn is raised with respect to the inner one. Theta is known as the angle of banking. And remember, the force of friction between the tire and the road surface is neglected. So, this is the center of the mass. The force acting on the vehicle would be its own weight, that is mg, where capital M is the mass of the vehicle. Now this road will obviously exert a reaction force. Reaction force always acts normally, that is perpendicular to the surface. This is the surface. So reaction force will be perpendicular to this surface. So it will be like this. This is the reaction force. Right? This is the reaction force. Now this reaction force can be resolved into two components. One in a direction opposite to mg. This can be easily proved to be equal to angle theta, right? It would be same. Now, how it can be verified? If you draw a horizontal line over here, then mg could be resolved into two components. So this angle is theta. So this angle is theta, and this angle would be also theta, being vertically opposite angles, isn't it? So this is theta, so this will also be theta. So one of the component which is opposite to mg would be r cos theta, and the other component which is directed radially inwards, it is r sin theta. This component is directed towards the center of the circular track and it is directed radially inwards. And students, this is a very, very basic fact. The force which is directed radially inwards always provides the necessary centripetal force. So here, although friction between the tire and the road surface is assumed to be neglected, yet the component of reaction, that is r sin theta of this vehicle, will provide the vehicle the necessary centripetal force. While on the other hand, the component of the reaction r cos theta, that will balance the weight of the vehicle, right? So mathematically, r sin theta, this component of reaction being directed along the radius towards the center of the circular track, that is acting radially inward, will provide the necessary centripetal force. At the instant when it is taking the circular turn, suppose its velocity is v, and r will be the mean radius of the circular track, right? So centripetal force is mv square by r. And as I told you, r cos theta, it is equal to mg. Along the vertical direction, the vehicle is under the influence of balanced forces, right? So if we divide these two, what do we get? R get cancelled, so sin by cos is tan theta. It is equal to v square by rg, or v square is equal to rg tan theta. Therefore, v would be equal to square root of rg tan theta. So in case friction is considered to be neglected, then the maximum speed with which the vehicle can take a circular turn on a banked road is square root of rg tan theta, without skidding or slipping or without overturning, right? So mathematically it is more appropriate to write like this. The safe value of the velocity which the vehicle can possess can be written like this. V is less than or equal to. This is the maximum value. So this is the result. Right, students? In some of the numericals which we can encounter in the coming session, there the height can be easily determined, right? Provided the other values are given. So let us find out an expression in terms of h and the width of this road. Suppose b is the width and h is the height through which the outer edge of the circular track is raised with respect to the inner one. So over here, students, v square is equal to rg tan theta, isn't it? So v square is equal to rg tan theta. It will be perpendicular by base. So what do we get is h divided by, use Pythagoras theorem. So what will be the base? It will be equal to b square minus h square, right? So it is b square minus h square. Now this h, in practice, h is very small as compared to b. So in practice, h is very small as compared to b. Therefore, h square can be neglected as compared to b square. Therefore, b square minus h square can be approximately written as b square. Thus, we get v square is equal to rg h by square root of b square, or v square is equal to rg h divided by b. Therefore, the height through which the outer edge of this band circular track is to be raised is given by b square divided by r into g. So this is the expression for h in terms of r, b, v and g, right? B is the width of this circular track, circular band track, right, students? Okay, now let us consider the case of banking of curved roads when the force of friction is taken into account. That is, when the force of friction is taken into consideration. So here, obviously, we'll consider mu to be the coefficient of friction between the two surfaces in contact, which in this case would be the tire and the road surface. And in addition to that, as we have discussed in the previous section, a component of reaction force that will also contribute towards the centripetal force, right? So let us consider this article. Again, let me repeat the intro. This is a car or any vehicle of mass capital M, right? And this is banking of tracks. Theta is known as the angle of banking. Banking of tracks means the outer edge is slightly raised as compared to the inner one. So let's consider the forces acting over here. Suppose this is the point where I will represent all the forces to be acting at this point, right? This may be considered to be the center of mass, where the entire mass of the system may be assumed to be concentrated. So one of the forces is weight, which always acts in the vertically downward direction. It is mg, no doubt regarding this. Then the ground will exert a normal force on the vehicle, and normal force means it should be perpendicular to this surface, right? So it will be like this. This is the normal reaction force. Clear? If theta is the angle of banking, then if you resolve r, it can be resolved into two components. This angle would be also equal to theta. This angle is equal to this angle. So this component is r cos theta. As we have discussed earlier, the component of the reaction r cos theta will balance the weight of the vehicle, right? And this component, it is r sin theta. This is the component of the reaction r sin theta, which is acting along the radius towards the center of the circular track. That is, r sin theta is acting in the radially inward direction. So definitely, this component of reaction r sin theta will provide the vehicle the necessary centripetal force. This we have done in the previous article, where the force of friction was considered to be negligible, right? This is the figure which we have done previously as well. Now, in addition to these forces, we have to represent the force of friction as well, right? The tires of the vehicle will tend to go in the outward direction, so the force of friction will act tangentially, parallel to the surfaces along this direction, right? So this is the direction of the force of friction, like this. This is F. This is also F. So of all the tires, the net force of friction, it will act parallel to the surface in contact and tangential, right? Down this, in this particular direction. So I will elaborate it with the help of this diagram. Suppose this is the point, this is angle theta, this is where the force of friction acts along this direction. Now what to do is, this is horizontal and this is vertical. So this angle will be also theta. So F can be represented, or rather small f, the force of friction, can be resolved into two components. One along this direction, it will be F cos theta, and the other in the downward direction, it is F sin theta. Now is it clear, students? So F cos theta, this component of friction, is also acting in the radially inward direction. So R sin theta along with the component of friction F cos theta, both acting in the radially inward direction, will provide the vehicle the necessary centripetal force. While in this case, if you consider the force of friction to be present, then R cos theta must be balancing mg plus F sin theta. F sin theta is acting in the downward direction, so it will aid its weight mg, which will in turn get balanced by R cos theta. Right? So you can represent this diagram over here as well. So F can be resolved into two components. This component of force, it is F cos theta, isn't it? And the downward component of the force of friction, it is F sin theta. Clear? Now let's try to construct the equations. Again I am repeating, students, concentrate on R sin theta and F cos theta. Both are acting in the same direction, that is in the radially inward direction. So in this case, where we are considering the force of friction, there the component of the force of friction F cos theta along with the component of the normal reaction, that is R sin theta, both being acting in the radially inward direction, will contribute towards the centripetal force, right? Therefore, first equation is r sin theta plus f cos theta. It is equal to mv square divided by r. V is considered to be the velocity which the vehicle possesses while taking this circular turn or while executing this circular track, right? And r is the mean radius. It is arithmetic mean of the inner and the outer radius. So, you can put this as equation number 1. In the vertical direction, the vehicle is under the influence of balanced forces. So, net upward force would be balanced by the net downward force. Therefore, the second equation would be r cos theta, which should be equal to f sin theta plus mg. You can modify it. You can write it like this. R cos theta minus f sin theta is equal to mg. Put this as equation number 2. Right? Now what to do is, let us divide these two. First, divided by second. Left hand side, what we get is r sin theta plus f cos theta divided by r cos theta minus f sin theta, and on the right hand side m will get cancelled, so we'll be left with v square by rg. Isn't it, students? Now what to do is, let us divide throughout the numerator and denominator of left hand side by r cos theta, right? So dividing RHS by r cos theta, both the numerator as well as denominator, both the numerator and denominator, right? What we get is r sin theta divided by r cos theta plus f cos theta divided by r cos theta. So we have divided the numerator by r cos theta, right? Similarly, in order to compensate it, we have to divide the same r cos theta with the denominator as well. That is r cos theta divided by r cos theta minus f sin theta divided by r cos theta. So here it is v square by rg. Okay. Now what we get is r get cancelled, so sin theta by cos theta is tan theta plus f by r, cos theta get cancelled, f by r is mu. Because we are aware mu is the coefficient of friction, it is equal to the ratio of the force of friction to the normal reaction. So here f by r is mu, cos theta get cancelled. Over here r cos theta get cancelled, we get 1 minus f by r is mu, and students, sin theta over cos theta, that is tan theta. So it is equal to v square by rg. Therefore, v is equal to square root of rg mu plus tan theta divided by 1 minus mu tan theta. So students, this is the maximum speed with which a vehicle can take a circular turn on a banned road, provided the force of friction is also taken into consideration. So this is the expression for the maximum speed, right? So actually mathematically we can make use of inequality sign. So it should be like this, right? It is the maximum speed which the vehicle can possess. So it is more appropriate to make use of this mathematical symbol. It is less than or equal to this speed. Now how to check whether the expression which we have obtained is correct or not? How to cross check it? Just remember the expression which we have obtained in the previous case, when the force of friction was neglected, right? There the formula obtained for velocity was square root of rg tan theta, isn't it? So here putting mu is equal to 0. In case force of friction is neglected, then mu would be equal to 0. then V would be square root of Rg mu 0. So we'll be left with tan theta divided by this term entirely gets 0 divided by 1 would be this only. So this is the expression which we have obtained in the previous case where the force of friction is considered to be negligible. Right? So this is how you can cross check this formula. So students, we are over with this particular session. This was a very important topic. So we have done 3 articles, right? Motion of a vehicle on a circular turn on a level road, and then we have considered banking of tracks. And here we have considered 2 sub-cases. One is when the force of friction is neglected, and the second is when the force of friction is taken into consideration. So I hope you have enjoyed this session, right? So do join me in my next lecture then. I will be coming up with some new very interesting topics. Right? Till then, goodbye and do take very good care of yourself. Always stay blessed.